Okay, so hello everyone, am I audible? Please confirm. Hello, hello,
Yes, sir, yes, sir, audible.
audible, right? Okay, good. Yeah, a few students are actually joining now, so I'll mm, check for them. So there are 11 of them. Okay, so let's get started then. Very good evening to everyone present over here, and thank you for joining. In this new NPTEL PMRF TA session on this course named Real-Time Digital Signal Processing. As you all very well know that this is a rerun of a course, but this is the first run where these PMRF sessions are being conducted for this particular course. So, my name is Shouharda Ghosh, and I'm currently a PhD scholar at the Electrical Engineering discipline of IIT Gandhinagar, and I have also done my dual degree, both BTech and MTech, in microelectronics and various design from the Department of Electronics and Communication Engineering at IIT Kharagpur. So please let me know in case I am not audible, or in case in the slide or my video, if anything is creating an issue, any interruption, please let me know. Okay, I will look into that issue and try to solve it as fast. So I need active participation from the student side as well. So just confirm once again, am I audible? Hello.
Yes, you are audible.
Audi- I'm
Yes,
au-
yes, sir.
yeah. So are the slides visible? Is the slide visible where my name is written?
Yes, sir.
And the slide is changing. You can see the slides are changing.
Yes.
Okay, okay, very good. So I think we can. It's a good time to get started now. So basically, before proceeding deep into this course right now, I would like to give some disclaimer, or rather some prerequisites before we proceed into this journey. Is that first of all, this course assumes that you have some decent knowledge of signals and systems, as well as digital signal processing. So we would be moving into the more advanced regimes of these topics which you have learnt in signals and systems as well as digital signal processing. Apart from that, as you will see later, this course is more of an application oriented course rather than being a completely theoretical course with which is full of mathematics and inferences and analysis. These you may see some of them in your assignments, uh, and we will also try to solve a few problems and question and answers in the upcoming sessions. But being an application oriented course, I feel it's always necessary to make you aware of the state of the art happenings related to this field. For example, uh, a few people and the people are joining as well. Okay, so for example, let's talk about. Let me introduce my field of research work. Actually, I am working at the intersection of VLSI as well as digital signal processing. So that's actually called VLSI for signal processing. So basically, I design VLSI structures in ASIC, as in ASIC, in which called application specific integrated circuits for signal processing algorithms. We very well know of FIR filters, IIR filters. We have all studied them, right? We also studied FFT, DFT, and various other kinds of image processing and other kinds of algorithms which we do in theory. Now the thing is that these algorithms are, at the end of the day, have to be used somewhere, which means they come in use in our real day-to-day life. So they must be implemented somewhere, right? So where do we implement them? There are various levels of implementation, which I'm sure you have also gone through in the first or the second lecture of the week, right? So over there, madam taught you about the various implementation possibilities, such as either the hardware or the software. So when it comes to the software, you basically write some code in MATLAB or let's say Python, and then try to run it in your general purpose computers, general purpose microprocessors, and then when you want to go deploy it some particular, let's say, application, maybe for some medical application you want to put in a device, or let's say some extreme applications, for example space application. You want to, you have seen this Chandrayaan 3 has just been launched, so there are lots of processors in it. For example, image signal processors chips are there embedded in the onboard module of that satellite, which takes in images and processes them and sends it back to the base station over our ISRO telemetry centers. So uh, okay, so what happens is that depending on the type of platforms in which you implement these algorithms, you have to play tricks with them. I mean, for example, when you try to implement it in some kind of a embedded device, or let's say you are hearing about wearable electronics. I mean, where the sensors are embedded in your shirts, t-shirts, and and it gathers data, and you process it inside the device itself. Now you can very well understand that these processing algorithms have to be very much power efficient or and area efficient. So sometimes it so happens that we have to modify these algorithms in such a way that you try to meet the application specific requirements. Okay, so now let's get deep into the course. So why I have talked all about this is that apart from the from the weekly assignments, we'll be solving some questions. We will also be reviewing the contents of the week, whatever has been taught in this particular week's module. And apart from that, I will try to show you certain state of the art developments every week based on the current scenario, the current technology. Okay, it can be maybe machine learning or deep learning implementation on our processors. It can also be something related to 5G, 6G, communication systems, or maybe some other kind of work that has that is being implemented, but that's not directly visible. So where do we see them? We see them in the research papers. So maybe we can have paper discussion sessions as well. We will show you IEEE papers regarding some of the algorithms which we learn in this course. And as it's an open-ended forum, all of you are very welcome to present your views or your interests. If you want me to talk about something, if you want to have a discussion session maybe related to something new that we have seen, something that's happening in the industry or research, or something that's boggling your mind, you are free to present your views in this session. It's an open-ended session, so unlike the lectures where it's a one-sided conversation, this is a two-sided. You can get your doubts solved here. We are all there for you, and we will also learn new things together as well. Okay, so let's dive and get in deep. So a bit is the slide changing? Are you able to see the new slide? Everyone there?
Yes, yes.
Yeah, so is the slide visible? I guess there's some kind of black thing happening, right?
Yes.
Okay, so let's get into the brief motivation of this course. So basically, as it's already mentioned over here, the course is designed to enable everyone, engineers, students and teachers, to be good signal processing engineers. And by signal processing, I don't mean the signal processing that's just done on pen and paper. It means signal processing which you do in real life. Because where do signals come from? It comes from the outside world. And where do you implement them? You implement them on physical hardware devices. So you need to have a good understanding of both signal processing as well as a bit of circuits and systems. I mean to say, you do not need to exactly go down to the transistors and their deep equations and quantum mechanics and stuff, but you need to have a brief kind of understanding regarding the architectures, how you are going to use these transistors, how those logic gates are being built up into adders, multipliers, and how those adders, multipliers and other arithmetic units work in an orchestric manner to give your desired output. Okay, so now this real-time signal processing, it's mentioned that it gives hands-on experience on the signal processing platforms, but since this is a review session, I will unfortunately not be able to present anything regarding the practical implementation of these structures. For example, you might have seen the code composer studio or these things. This will not be presented. I will mainly be talking about whatever can be done in the theoretical aspect, as well as the research, as well as industry aspects, but not anything practical. I will not be showing any embedded processors or something, live demos. That will not be done over here. So that's a clear cut no in this session. And basically this course is divided into 3 modules: signal analysis and filters, frequency domain or spectral domain analysis, and then applications of RTSP. All of them one after other, they have been put in such a manner so that you can see we have learned the basics of the signals, how you analyze the signals, and then the filters, the basic operations of the filters, and then when you build up upon module 1, we use that information and knowledge into the second module, where you use the acquired signal, analyze the signal in detail using spectral analysis, because you have learned very well from your previous signal processing classes that you may not be able to analyze everything in time domain. That's why frequency domain analysis is very important. And then based on the various kinds of frequency domain analysis techniques, we will later learn how to apply those techniques, as well as some other kind of algorithms, how they're applied real-time signal processing. Now a very important thing to understand is that term called real time. Okay, it's not signal processing, it's real time. So it means you are getting the data on the fly, which means that you are acquiring the data and you have to process it on spot. So it doesn't mean that the algorithms that you normally do in MATLAB, you create some kind of an array, you create some kind of an artificial signal and then process on it. So that's like stored, you are storing the data already and working on it. But then over here it's significantly different. You are processing the data at one go, and if you lose the data once, a few more people want to join. So if you want to put in the data once, if you lose the data once, then you lose it forever. You have to manage it on the spot. Okay, so now we get into details of the further modules. Yeah, so the first module, that is signal analysis and filters. So in the week 1, I think most of you have already seen these lectures. So it talks about the basics of the RTSP, as I talked about along, and then it talks about the number systems. What are the basic number systems? The floating point and the fixed point. When to use it, when not to use it. As you very well understand, floating point system. Okay, so let me let me throw it as an open question to you. So when you are doing your MATLAB programs, when you are implementing some FIR filter, IIR filter, or some kind of multiplication division on your laptop or on your computer, what kind of an operation is that? Is it a floating point operation or a fixed point operation? Can anyone tell me?
Yeah, it is floating point operation.
Okay, so why do you say it's a floating point operation? Any brief idea? Okay, so you are actually correct. It's actually a floating point operation, because the arithmetic units that are being used in our processor, let's say Intel Core i3, Core i7, Core i9, all of them have floating point processing units, floating point ALUs. If you go to Intel's ISA sheet or their CPU processor, you will see 32-bit processor, 64-bit floating point, FPALU. When this word FPALU is mentioned, that means you understand it's a floating point arithmetic and logic unit. And its biggest advantage is that it gives you a lot of flexibility in the dynamic range as well as the precision. You can work with numbers ranging from 10 to the power minus 25 to 10 to the power 50 billions, a very big range you can understand, right? But then the biggest problem with this floating point number system is the hardware. The hardware is really power hungry. Okay, so for example, and it's power hungry, so you can never afford to introduce a floating point processor in maybe some kind of a pacemaker. Okay, because once you insert a pacemaker into a patient's heart, then you do not want to the patient to actually replace the batteries of the pacemaker, right? Until and every time it's really difficult to do surgery always, and nobody would like that. So what do you want? You want the pacemaker to run on the energy that is provided by the surroundings. So it should be a low power algorithm or architecture. So we will never use floating point architectures in places where there is a need for low energy low power implementation. Also, these are not used in places where you have area constraints. Like I told the pacemaker case, you also have hearing aids. Okay, so and there are some limitations on your chip sizes. So that chip size limitation also forces you to put some restriction on the kind of units that you can use in your system. So that's about. But you can use, you have used it in a processor. Why? It's a general processing unit. Yeah, anybody would like to say something? Somebody had put their mics on.
Sir, how can you say the floating point one needs more power?
Actually, the thing is that let's say when you have floating point representation, so you have three parts: sine, magnitude, and exponent, right? So let's say even when I have to do 2 plus 2, okay. So I guess okay. So actually, let me tell you, I'm not, as of now I do not have a proper pen, so you may not be able to get proper visible readings today. I mean, I will be writing quite less today, but maybe the next week or the next week onwards, you'll be getting proper writings in detail. Okay, so please bear with me. Sorry for that. A few of them are joining once again. Yeah. So let's say you want to do 2 plus 2. Okay. I guess it's visible. Now when you want to so when you want to do this in let's say a fixed point, I'm telling let me clearly tell this beforehand. Fixed point. So 2, let's say in 2's complement, you can represent it as 0, 1 and 0, right? Okay. So when you try to add these two numbers in fixed point, you can see it's a 3-bit number. This is also a 3-bit number. Now in order to ensure that your output does not overflow, so what we do is that we will do a sine extension. Okay, I hope you know this. In case you don't know, please let me know one second. What we so let me reiterate. Let's say you have an n-bit number, another n-bit number. When you want to add the two n-bit numbers, you have to ensure that your output does not overflow. So your output has to be n plus 1. Now in order to ensure that this one happens, what we do is that this is the sine bit, right? For the 3-bit number, the first MSB is the sine bit. Now what we do, we extend this into the left side. If it was 0, we copy it over here. Had it been, let's say 1 1 0, which is minus which in 2's complement is minus 2. Okay, so if I want to do sine extension, what will I do? 0 1 1, and I will again copy the MSB to the left. So it's a 4-bit number, but still if you see, you will get the value minus 2 only. Okay, so after doing so back to our calculation. So after doing 2 plus 2, you will get this kind of 1 plus 1 is 10. You get a 1, add over here 0 1 0 0. So you have seen, you can see very well that we have not done any overflow. Our calculation is absolutely perfect. So it's a 4. Okay, so you can see I have just worked with the 4 bits. Okay, now when you talk about the floating point units in your devices, in your, let's say in your CPU, these are let's say my laptop is a 64-bit using a 64-bit processor. So that 64-bit processor, double precision word length, so it will have some bits of mantissa, some bits of exponent. So you are working with all these mantissas and so many bits you are working with. Okay, and then the internal units, the mantissa, exponent and all their calculations, they also have to be manipulated. They have their own circuitry. This simple thing is that the circuitry for the floating point is extensively bigger and has higher number of units compared to a fixed point. Okay, so that's the reason why, because of the higher number of units and the kind of units being used over there, it uses a higher power. Actually, it is more to do with the internal logical structure of the floating point unit. In fact, if you want, you can refer to some kind of a digital architecture design book, maybe Barhu's Paramit, in order to check what are the floating point architecture looks like. Okay, so is that clear, Sampath?
Yeah, yeah, it's clear, sir. But you said dynamic range point of view, some
Uh-huh.
advantage there for floating point.
Yeah, yeah.
For example, if we see minus 127 to plus 126, otherwise 0 to 256, both are same, right? For
Hmm.
dynamic range point of view.
The one that we have mentioned is actually what is happening over there when you, okay, let me clear your point. So when you mentioned minus 120, actually it should minus 128 to 127. Okay, this is something called 2's complement. Okay, this is how many bits 2's complement? 64 is this. Okay, and the other one that you told was 0 to 256. Sampath, isn't it the same that you were asking for?
Yeah, yes, yes, yes.
So this is called the unsigned representation. Now the, oh sorry, it's not an unsigned complement, it's unsigned representation. Okay, so what is happening over here is that the number of bits in both the case are fixed. Okay, and both of them are actually fixed point. Okay, this is not floating point. So the dynamic range is same, but the dynamic range is same, but you can see the precision is the same. So actually it's not the floating point, it is the fixed point. But if you talk about, let's say, floating point, we don't have such small ranges of minus 120 to plus 120. We have maybe something like 10 to the power minus 32 to 10 to the power, I cannot confirm you 10 to the power 32. I mean, this is the kind of range that you will be able to get. Okay, like exponential gain. So that's why I was saying that the dynamic range, you can see this 10 to the power 30 is of the order of the,
Yeah, now I got clarity.
okay, understood, na? Because these are, both of them are separate, both of them are actually fixed point only. You are using 8 bits to represent both of them, but then uh, you can say that one of them is representing the entire positive space and the other one is symmetric around 0. Okay, that's the fixed point. And you can see, since I'm dealing with a finite number of bits, you can easily work with them, and the corresponding architecture or the logic gates, which you call, will be lesser compared to the floating point. You can see 10 to the power 32, so you have to deal with such big numbers. You have separate logical structures for them, but they are highly complicated. Okay, so let's get back to our presentation. So we had a good discussion of our number system, and we already just talked. It's thanks to Sampath that he, in fact, told us to revise the concept of fixed point as well as floating point. We have also seen the concept of sign extension. I hope everybody is clear with the sign extension. Does anybody need any kind of repetition in this, or any doubt in sign extension, because it's a very important concept? Okay, fine. And then we went to the DSP. We also studied briefly about the DSP architectures, where we saw there were 4 kinds of design. When one was the general purpose processing architectures, and then one was the application specific. So some of them were DSP processors, some of them were embedded systems, some of them were FPGAs, and some of them were ASIC chips. Okay, so each of these, I should say that there is no one solution fit all kind of stuff, that this architecture will fit everything. No, every application has its own requirement. The application which I told, let's say the pacemaker application requirements are much different compared to the let's say some kind of a network router which you use in your modems, or maybe the GPUs which are used in the data centers at Facebook and Google. Okay, so there's a clear kind of distinction between the architectures and their requirements. So based on your application, you'll be using the corresponding architecture. For example, let's talk about the kind of architectures that I work in. I specifically work in ASIC design. Okay, so basically what we do is that we have some kind of adaptive signal processing algorithm which we will be studying in our at the end of the let's say around week 10 or 11 we'll be studying adaptive signal processing as well as LMS algorithms as well, where we try to implement these adaptive signal processing algorithms on a chip which can be used in let's say hearing aids for because the hearing people have a lot of issues at the old age, and these days because after post covid people are using headphones. I am wearing one of them, and WHO has predicted that almost 50% of the population is almost prone to hearing related problems after 2020. So there is a trend to make your hearing aids more and more customizable, more and more power efficient, because you don't want to charge your hearing aid now every now and then. So how to ensure that you are able to hear good quality speech? Okay, there may be noise whistling around, but you have to ensure that you are getting the speech properly. So that's the signal processing aspect. But you also need to ensure that your hearing aid, the circuitry inside it, consumes as less power as possible while maintaining the same performance. Okay, so that's the ASIC design. When an ASIC designer designs these chips, he has to look at both the ends. Okay, so in DSP architecture we have also got a brief glimpse of the kind of this normal von Neumann architecture. Okay, and as well as the memory hierarchy, how it plays an important role in the signal processing systems. Whenever you have to whenever you run your codes, MATLAB codes in a processor, then you have to go through these five stage instruction processing cycle: fetch, decode, execute. Okay, so these were discussed. We will be also reviewing the slides once again. In week 2 we'll be talking about FIR filters. Okay, basic FIR filters. What are the kind of FIR filters? What are the different topologies? It's not that FIR filter is just a few finite tabs. Now these finite number of tabs, h of z, you represent them as summation of h of n z to the power minus n, right? I hope everybody has studied FIR filters. So those FIR filters, now a single FIR filter can be implemented in various ways. You might have learnt about direct form 1, direct form 2, transposition, and other kinds of architectures, some cascade of two structures, cascade of smaller and smaller filters. So these what happens over here? Now the signal processing part ends here, and then some advanced concepts of VLSI as well as a bit of signal processing comes into picture. Some structures may give you lesser noise, some structures may take lesser area, some structure may consume lesser power. So there's a mix and match of everything. So we'll be studying about that in the FIR filters after briefly reviewing them. And then there's pipelining and parallel processing for high speed / lower power applications. So how we utilize the concepts of pipelining as well as parallel processing, that will be briefly discussed in the week 2 lecture. I'll also be explaining you the derivation of certain things which we will be seeing in week 2. Week 3 and 4 will delve once again into IIR filters. You might be thinking that why are you just discussing filters and filters? We have already studied this in a undergraduate curriculum, right? But then the thing that I want to emphasize again and again is that these are the filters, these are the concepts which are being incorporated and utilized by the companies like Qualcomm, Broadcom, Samsung in all their chips. For example, we are having a face-to-face communication over this online Google platform. You don't know there are several transmission mediums, several processing that are going on at this very moment that you are able to see me and my slides as well. You are able to hear my voice properly as well. I hope my voice is clear once again. But there are lots of devices, lots of protocols, lots of algorithms being used so that you are able to get my voice. The communication happens clearly. So you can deep down into our networking systems, we have these FIR filters playing a very important role in this communication at this place. So you are not learning any dry subject, you are learning things that are being employed over here. And in fact, one very good thing about this course is that the contents of this course can be used in case you are sitting for placements of certain companies in the signal processing profiles. Maybe someday later I will try to show you the kind of signal processing profiles that various companies put up. So we'll be talking about IR filters, and apart from the filters and the structures and as well as those routine kind of stuffs, we'll be also discussing, since we are implementing these filters on a real-time platform. Since we will be implementing these filters, FIR filters as well as IR filters on our on our chip, so we will not be dealing with infinitely large infinite precision numbers. Let's say on our MATLAB or some Python, we, as I mentioned earlier, we work with 64-bit or 32-bit systems, but then we will be having finite bit precision. Based on that finite bit precision, we will have some loss in performance of these filters. Okay, now this loss in performance leads to degradation in signal quality. But now, how do you tackle them? How do you ensure to how many bits to keep in? What kind of internal manipulations you can play in your filter in order to ensure that your filters work very well, your performance is good? That will be studied in the quantization effects. Okay, quantization effects is a really important topic to be understood in terms of FIR as well as IR filters. Okay, so once we have learnt about the rudimentary basics of our signals and systems as well as systems, meaning these filters, we will learn about how to analyze the signals, the content of the signals. So as we have learnt in our undergraduate courses that there are tools like continuous time Fourier transform, discrete time Fourier transform, then Z transform, and many other transforms. There are other transforms which are not discussed in our courses, but they are also used. Let's say short time Fourier transform, which are used for different kind of manipulation of signals. Okay, but then there are certain we cannot implement all these things on the platform. Continuous time frequency transform, you can understand, it works with analog signals. And even if you try to work with analog signals, the frequency range is continuous. Now you can't, your computer has finite memory, you won't be able to store infinite numbers on your computer, right? So your computer is a finite state machine, your computer has finite memory. Now you have to do all the processing in your finite memory. Even your analog signal has infinite precision. You take a voltmeter or you get some kind of reading from a sensor, that's infinite precision. But then what happens is that in reality we have to quantize these values, we have to quantize these signals because of a finite space of a computer. So we use these finite space, finite duration signals, or let's say finite length transforms. Okay, discrete Fourier transforms, which works with some finite endpoints. Okay, we work with a finite length of signal. We may have, what happens is that sometimes our signal is infinitely long and we want to keep on analyzing this content of the signal. So what happens is that at every let's say at every 10 milliseconds or 30 milliseconds, we chop off the signal, take chunks of those signals and apply the signal and apply the spectral analysis tool, the FFT or DFT on that. We'll also be studying about the FFT, DFT. We'll do the DFT analysis, what is the complexity analysis, why it's so bad, and then move to fast Fourier transform, a very efficient implementation of the DFT algorithm. Okay, because DFT, as you will be studying later, has some kind of n square kind of a complexity, and then the fast Fourier transform then uses the divide and conquer approach that's used in a lot of algorithms. Those who have if you have studied algorithms in a past time, or let's say data structures and algorithms course, then you must have seen that whenever you want to do a big job, you break that into smaller pieces. That sub job, you break that into smaller pieces. That's what an FFT does. What it does, it's not a try to understand it. FFT is not a separate separate transform in itself. It's a more efficient implementation of the DFT. Okay, so FFT tries to break things into smaller groups and break things until you go into the smallest unit. Okay, we'll study more in the later courses, in the later weeks. And then in week 6 we'll talk about much more about FFT, like overlap add and overlap save. Okay, so now we go to the main portion, what we'll be studying in the final 5-6 last few weeks, that is the application portion. So first we'll study about a brief about signal correlation. What is the kind of let's say you have some kind of a signal, then how correlated are the samples of the signals to each other. You might have learned of the autocorrelation function, right? Now how do you exploit that kind of a correlation in order to get better compression? What happens is that, let's say you have a stream of data. Now your data has something like 127, 128, 127, 128. Now you can understand 127 and 128 can be represented as an 8-bit number, but then you're representing as an 8-bit number, so you're taking 8-bit registers. We'll talk more about registers soon. 8-bit registers, so there's more area. But then you see my data is oscillating between 127 and 128. So what will happen if I try to subtract 128 from the entire data stream? Is just zeros, plus ones and minus ones, right? So basically what you can do is that based on the correlation, how correlated are the data nearby, you can compress the data. Okay, so that's where compression comes into picture in correlation. And in fact, when we are having this online communication, there are compression techniques coming into picture that tries to compress these videos. If you are looking into your mobile phone, if you are not using laptop, you might be using a mobile phone for checking this online meeting now, so that uses some kind of an HEVC encoder which also does good video compression. That what it uses signal correlation. Okay, and then we'll be talking about adaptive filters. Especially adaptive filters is the place in domain in which I work. How the filters. In the previous session we had talked about in the previous weeks you will have learnt about the FIR filters, IIR filters, but then the problem with these filters is that their coefficients are fixed. They are fixed for once and all. You design a low pass filter with some kind of a bandwidth, pass band, stop band. The design is done. You cannot change things anymore. If you change a single value of the filter coefficient, your entire performance is gone. And let's say suddenly you want to change your signal based on the signal, you want to tune your filter performance, then that may not happen in the normal FIR filter. You have to again design. So adaptive filters are a different class of filters. What do they do is that based on the signal, okay, based on the statistics of the signal, not just the signal but rather the signal statistics. By signal statistics we'll be concerned about the mean of the signal, the variance of the signal, some kind of a correlation measure because of which we will be teaching signal correlation before that. Those kind of statistical measures will be taken to change the filters on the fly. Okay, and a fun fact for you, adaptive filters is also a kind of machine learning algorithm. In fact, if you know about machine learning algorithms, it's a kind of supervised learning algorithm. We will have some desired signal, and now based on the desired signal we will try to adapt the filter coefficients so that our input signal is processed and being adapted so that we get the desired signal performance. Okay, and sometimes it so happens that we may not the desired signal will be some kind of a noise. Okay, you have noise cancelling headphones. So what happens in noise cancelling headphones, we'll be talking about that in adaptive filters. Okay, and in fact this is one of the things in which IIT Gandhinagar, the lab in which I work, audio signal processing lab, in which we do work on. We also work on adaptive filter processing, signal processing, and some kind of noise removal stuff, active noise removal, how we use them in our music systems, cars, automobile systems. Okay, then in week 8 we do a continuation of the adaptive filters where we learn about the least mean square LMS algorithm. It's a very famous, very important to know algorithm if you are going to be a DSP engineer. Okay, and then we'll learn about the applications, how you implement them in a LMS. If possible, I shall also show you some kind of an implementation of least mean square algorithm on hardware, how it will actually look on hardware. By hardware I mean to say on an ASIC chip. I'll be showing the detailed structure. Then week 9 goes more into an application specific domain, echo and graphic equalizers, which I guess you have seen equalizers in your mobile phones or stereo, where you kind of adjust the knob automatically, and based on the adjustment of the knobs you can try to tune the filter coefficients. Just like in the olden days we used to have the radio, you can tune the knob. Now what happened in knob, there was a capacitor, you used to move the capacitor, and based on the capacitor value there was an LC tank RC filter, LC tank oscillator, and that used to tune with the frequency of the radio, let's say 93.5 FM or some kind of that signal, the carrier signal with which you are tuning, and based on capacitor value you are tuning to a particular channel. Similarly, here also you have a knob, but that knob is not a capacitor. You are simply trying to change the coefficients of a filter and trying to adjust the kind of voice you want to hear. Let's say you want to you are using a phone to listen to music, but you want to get some kind of a auditorium experience. You want to hear tabla, you want to hear the reverberations that happens in a auditorium to give you a good quality experience of the music. So you have those knobs. You can switch just with a click of a single button. You will get the experience of an auditorium. Now what happens actually in the experience of the auditorium, how you will able to get that? In reality, the auditorium experience, the reflections can be modeled by a impulse response. See, I am using a concept of signals and systems to explain what happens in your mobile phone. Your room, our communication, the auditorium's reverberations can all be modeled by an impulse response. And when I say can be modeled by impulse response, you can represent it in the form of a fire filter. So basically what happens, the program tunes the coefficients and gives you that kind of a response. So maybe later after you complete this course, you might be able to design your own equalizers or code something out and give some kind of rock experience in your some kind of a bland music. Then in week 10 we talked about speech coding. Speech coding I just talked about in week 7, signal correlation, which I have told that how the samples, how the signal samples may be correlated with each other, and then how you can use that to compress your data and so send lower and lower bits of data and achieve higher throughput. Then in week 11 we will be talking about a discrete cosine transform, which is a very important algorithm for image compression. Why image compression? Because you can transform it to frequency domain and do lots of stuff with this discrete cosine transform, which we will discuss in week 11. And week 12 is mostly about lab sessions and implementation of RTSP algorithms. So as I had mentioned earlier, some of the important implications of these real life applications of the signal processing as algorithms. For example, digital voice assistants. So you have heard about Amazon, Alexa, Echo, Google Siri, and all these digital assistants to which you speak, and then these assistants use their AI algorithms to reply. But then there's a signal processing aspect to it. What happens is that, let's say you are at some corner of the room, and then there's Amazon Alexa on the Amazon Echo on the other part of the room. Okay, so how it will ensure that you are where you are? So it uses some kind of technique called beamforming. Okay, we will not be discussing much about beamforming, but if you want, I can share maybe in some later time I can share some paper and discuss how beamforming happens. So it uses a beamforming technique to first locate where you are, where the voice is coming from, and based on that it locks into your position, and now if you try to move here and there, then it will lock into your range, and then it will be able to gain your signal. That's all signal processing. Health monitoring, and here I have specifically given the image of a fetus and its heart. Okay, so you can understand very well that a fetus is inside mother's womb, and you are trying to acquire the heart signals in order to understand the health of the fetus. So you can very well understand that the fetus signals and that the fetus heartbeats has to pass through a lot of environment tissues and environments and then reach the sensor. But apart from that, there are a lot of other noises that are interfering with the tissue with the fetus's heartbeats. For example, the mother's own heartbeat can interfere with the child's heartbeat. Okay, so you can understand there's an interference, right? Now if you try to directly put one sensor in it, and what will happen, I will not be able to get proper signal. I will do some kind of a misdiagnosis. So what is the solution? So we just see over here, we mentioned in our previous slide about adaptive filters. So what we do, we use an adaptive filter in which on one side we try to take the mother's heartbeat signal. Okay, one sensor for mother's heartbeat signal, another sensor which is gets granted goes to the fetus. So we we try to acquire the mother signal and try to cancel it with the signal of the fetus's heart signal, the kind of signal that you're receiving, and at the end you cancel the interference, and then you obtain the desired signal. But it's not that easy. There are lots of as you can understand very well, there are lots of different paths through which these signals transfer. So how do you model the paths through which these signals transfer? That's done by your adaptive filters. In the meanwhile, if anybody has any question, you can interrupt me. Okay. So and apart from that, now the buzzword in the telecommunication industry is a 6G. So a lot of things like pulse shaping takes place. Pulse shaping. I also talked about beamforming in the case of digital voice assistants. That also takes place in your 6G telecommunication. And apart from that, there's some kind of a non-conventional branch of signal processing which does not directly deal with some kind of sensor signals. It is the algorithmic trading. So there are high frequency trading firms which uses our classic as well as non-classic signal processing algorithms in order to predict the upcoming, let's say, stock prices or market share values, and then based on the prediction we put on bets on that. So algorithmic trading is also an application of signal processing. They use some kind of filtering or some kind of an estimation, the classical estimation algorithms that we talk about in estimation and detection theory, the filters, the windowing techniques that we learn in DSP. That's also being used in algorithmic trading, and I'm sure, I guess, you will find it interesting. Okay, so now we shall move into some problem solving sessions in which I shall be asking first I shall be asking you to answer, and then I will explain it on my own. Okay, I shall not be writing much today. Maybe from the next week I shall be writing in detail. Okay, so here's your first question. In a DSP processor, are the writings visible? Can anybody confirm, or it's too small?
Yeah, yes, visible.
Visible, right? Okay, so let me repeat the question for everybody's benefit. I also want others to participate actively because this is an interactive session. You also get to clear your doubts from my side. Okay, so in a DSP processor, if an operand A has m bits and the operand B has n bits, they must be multiplied. Okay, so a multiplication, as you very well know, is a very important operation in DSP processors. In any DSP algorithm, you will be able to see multiplication happening everywhere. So it is fundamental to know what happens in the multiplication at the architecture level. So when these two numbers with m and n bits respectively are multiplied, what is the maximum number of bits required to represent a product? Can anybody answer this question?
M plus n.
Okay, so you are absolutely correct. Let me show you the reasoning for that. Okay, so these are the copy of the slides that had been taught in the first week. So what happens is that, as you can see very well, I don't have to explain much. Here in this case we have assumed that A and B are both unsigned numbers. So it has been assumed that r bit that this product has been r bits, so it's in the range 0 to 2 to the power r minus 1. Now the minimum case, since it's an unsigned number, the minimum case that you can take is 0 and 0. A will be 0 and B will be 0. That gives you 0. And when it is maximum, that's 2 to the power m minus 1 and 2 to the power n minus 1 based on the ranges. And when you multiply them, you don't get you get some kind of a number 2 to the power n plus m minus something like this. That is your. Now one thing to note is that when you are multiplying, let's say, a 3-bit number with a 4-bit number, okay, the maximum that a 3-bit number can take place in unsigned number is 2 to the power 3 minus 1, okay, that's 7, okay, and the other one is 2 to the power 4 minus 1, that's 15. So when you multiply that highest possible 3-bit number with the highest possible 4-bit number, that does not necessarily mean that when you multiply the two, all the resultant so-called 7-bit number 3 plus 4 7-bit number will be all ones. Okay, but still, in order to ensure safety, we have to go to maximum. Your maximum may be when I said 5 into 17, so that may not take 7 bits, but then in order to ensure that your algorithm is safe, you have to get the maximum number of bits. Okay, so that's why, based on the kind of approximation that has been shown, it's an m plus n bit number. Okay, so now the second question, that's in a 4x4 Braun multiplier, what are the number of adders? So everybody can try this out and let me know what's the answer to this. In the meanwhile, if anybody has any doubt, you can ask me.
None of the above, sir.
Yeah. Okay. So So what is the correct answer as per your if if none of the above, but it has to be something. You can't have an empty multiplier. So what are the number of adders, half adders, full adders, that you feel is correct? Yeah, Chintu Yadav, you said none of the above. So what is the actual number of adders that that are to be used?
16, sir.
Okay, let me show you actually what happens. I got the idea where you're telling 16, but let me show you. What happens in reality is that, oh sorry, can you see the A0 B0 part, right? Hello, am I audible?
Sir.
Huh. So
Yes, sir.
so what actually happens over here is that if you ask me to count, so the general kind of processing element which is being shown over here in red, everybody can see in red, it's the full adder. Okay, but then in the figure, what you can see over here is that there are some 0 0 0. Okay, there are zeros in the first three adders, and then there's a 0 in the last adder. Okay, the adder just above P4. Are you able to see P4? The term P4, can you see the term P4? Can you anybody please check Airtel if the image is visible? Hello. Yeah, is the image of the Braun multiplier visible? Can anybody please confirm?
Yes, it is visible.
Okay, so Sampath, above P4, can you see an adder?
Yeah, yes, sir.
Yeah,
That
so
zero is
0 is there, 0 is visible, right? So as you can see, there are three adders in the first row which have a 0, and then the adder of the last row just above P4, that has another 0. So when you just add, so adding a 0 means adding nothing. Okay, so at the end of the day, what happens is that you are adding two numbers, two bits actually. Note that this A0, A3, B3, these are not whole numbers, these are pure binary bits. It's either 0 or 1. It's the end of the two bits of A and B. Okay, so when you are adding two numbers over here, so rather than a full adder, we call it a half adder. Okay, so here we are using 4 half adders, and there are a total of 1 2 3. There are 3 in each row. There are 3 adders, and there are 4 such rows, so there are a total of 12. There are let me write it down over here. There are 12 adders, out of which you can see there are 4 adders which has 0 input. Okay, the input 0 being given, so there are correspondingly 4 half adders, and then rest 8 full adders. Okay, so let me write it down for you in this thing as well. So let me actually clarify what had actually happened. So when you, let's say, multiply A3, A2, A1 and A0 with B3, B2 B1 and B0. So what happens is that is this A0 and B0, when you directly do A0 into B0, this one does not go into any half adder or full adder. Okay, it directly goes into the for lowest bit of the product. Okay, that's why this rather than having four terms, like rather than having four adders in my first row, I have 3 in my first row. So consecutively I will also be having 3 such adders in them. Okay, and then we shall be adding all of them. Okay, so going back to our diagram. So I hope everybody is clear with this. Does anybody have any issue with the Brown multiplier? Yeah, so does anybody have any issue with the Brown multiplier over here? No, Sampath, am I audible?
Yeah, audible, sir. No issues.
Okay, okay, no issues. Then I am proceeding forward. I need some active participation from other participants as well. Okay, so now the next question is, why is scaling preferred? Scaling is preferred due to option A, the trade-off between overflow prevention and accuracy. Second one is to increase the dynamic range, and third one is to increase precision, and fourth one is none of the above. So somebody else, can you please tell me why is scaling preferred?
I think option B.
To increase dynamic range. Okay, so that's what you are trying to say.
Yeah, yes, yes.
um okay, so why not option C or option A?
For example, if I want to measure any value of
Hmm.
any instrument, it
Hmm.
ranges from 0 to higher value.
Hmm.
Um, for example, my hardware is limited to some dynamic range.
Hmm.
Can I scale that in then it a bit? Then I can get I can correlate with the dynamic range.
Okay, so it seems that you mean to say, let's say you are connecting something from 0 volt to 5 volt. Okay, and let's say I have 1 volt division of that. Okay, now let's say you try to scale that. Let me take out. Yeah, okay, so let's say you have a number, you have your voltmeter or some kind of a device that measures from 0 to 5 volt, and in intermediate it measures 1, 2, 3 and 4. Okay, now what happens is that, let's suppose I scale this by a factor of 2. Okay, so I'm scaling it by a factor of 2. Now you see what happens. 0, by scaling I mean I scale down. Okay, I've given this arrow for this reason. 0, 5 by 2 is 2.5. So 1 goes down to 0.5, 2 goes down to 1, 3 goes down to 1.5, 4 goes down to 2, and let's suppose I scale it upward by a factor of 2, the original one. Okay, let me change the color. I should have made this one in green. So when I scale these from here to here, I get 0, 2, 4, 6, 8 and 10. Okay, so can you see something over here? When I have scaled down, from 0 scale down by a factor of 2, my dynamic range has decreased by a factor of 2. From 0 I can measure up to 2.5, but my precision has increased. I can measure 0.5 volt by a more precision. I have gone made my precision up by a factor of 2. I can measure 0.5 volt signal, which I was not able to measure earlier in my previous range. Okay, 0 to 5 I was able to measure only in 1 increments of 1, but here I am able to measure increments of 0.5. So I have reduced my dynamic range at the cost of higher precision. Now you see the other case. Over here I have increased my range, okay, 0 to 10 volts. Now I can go and measure even higher voltages that I was not able to measure earlier with my instruments. Okay, maybe I have done something good in my voltmeter, but then you see the issue. You can measure from 0 to 2 directly. You cannot measure the 1 volt that you were measuring earlier. Okay, you are going by steps of 2, 4, 6, that you have increased your range, but at the cost of lower precision. So can you see a trade-off over here? So
Yes.
absolutely. So there is some kind of a trade-off. Okay, whenever I will talk about trade-off, I will use this seesaw structure. Okay, trade-offs are very important things in an engineer's life. You have to trade off one thing for the other, because there is nothing called free lunch. So you have precision, let's keep it precision, and yes, dynamic range. Okay, so there's a you can clear cut trade off between your precision as well as your dynamic range. Okay, so there's a trade off between precision as well as dynamic range, but here is written trade off between overflow prevention as well as accuracy. Now let me clear this out for you. The accuracy thing is similar to that of the precision. Sorry. So what happens over here is that, let's say when you are that's one aspect of this thing. The other aspect is that, let's say your hardware is not just measuring voltages. You have to remember this is a signal processing course, and so you will be performing operations on that. So the perspective that you were talking about was partially correct, because you were talking about measuring instruments, but then we are actually doing the scaling in the signal processing operations. We are doing addition and multiplication. Okay, so you need to keep that in mind, that we are doing operations as well. So based on that fact, you can see that when you are adding 0.5, okay, when you have done some measurement, or so there is some signal, let's say x, by default let's suppose it represents 1 on my previous scaling normal scale. Okay, I saw it as normal scale, and when I decrease it by a factor of 2, this signal is actually represented by 0.5. Now when I do, and my hardware is actually fixed. Okay, so x, y. So when you do x plus y equals to 1 plus 2, that's 3. Okay, and now when you have lower precision, you do x plus y equals to 0.5 plus 1, that's 1. Okay, there's, and when you are working with lower and lower numbers, there are lower chance of happening overflow. Now you remember what I mean by overflow. When you have, let's say, a 4-bit number, that, let's say, it's 15 in unsigned. Now 4-bit 15 plus 15, that's 30. Now you cannot represent it in 4 bits, right? Clearly, why? Because this is an overflow that is taking place. But if I scale this down by a factor of 2 and still use our 4-bit number, what happens? 7.5, 7.5, 15. So we are getting that number. Actually, since we are staying in 4-bit number, what will happen is that this 0.5 we cannot save. So what is happening, you can understand, we are storing it in a 4-bit word, and we are representing it in integer format. So when you are scaling it down by a factor of 2, we will divide it by 2, but then we cannot represent 0.5 in our 4-bit integer. Yeah, is everybody understanding this point? Because it's very crucial for designing hardware. Please tell me if you are not able to understand this point, what is happening. Am I audible?
Yeah, yes, you are on.
So you are able to understand why I am not able to represent 0.5, what is happening over here?
Yeah, we understood.
Yeah. So because I can represent only 4-bit integers over here. So when I am dividing by 2, I'll later tell you what the divide by 2 means in hardware. So we cannot represent it by 7.5, it becomes 7. So rather than 7.5 plus 7.5, we actually end up with 7 plus 7, and that yields us a 14. Now you see what has happened over here. Now if I want to gain back my original number, I will scale it back by a factor of 2. Okay, so what's 14 into 2? That's 28. What will happen is that I will store it as 14 in my 4-bit register, but outside when I will see this 14, I will multiply that by a factor of 2. That's something called scaling factor, which we do not explicitly show or use in our hardware, but we keep it reserved with ourselves, with the programmers. Okay, the programmer or the hardware designer has to keep a ready reference for the scaling factors, so that whenever he gets internal variables in these registers, he will be able to obtain the original value by multiplying by the scaling factor. Now you see what happened. I was supposed to get 30, I got 28 now. Okay, so what happened, I saved myself from overflow. Had I been doing it without scaling, I would have obtained an overflow and got a 30. But then when I tried to do scaling, I was able to prevent this overflow from happening by saving it in a 4-bit representation. But then at the cost of this saving this 4-bit representation, I lost accuracy. Rather than getting 30, I got 28. Okay, so that's why the correct answer to this is trade-off between overflow prevention and accuracy. Okay, now I hope you have understood what I have tried to show, that when I am using scaling, that time I have saved myself from the overflow taking place due to addition, but at the cost of accuracy. So in these slides, so there's option A. Okay, Sampath, I hope this is clear. You understood why this one is correct.
Yeah, it's clear, sir.
Okay. Others as well, please respond if you are having still any doubts. If you are still having any doubts, please let me know. Okay. Okay. So basically in the slides, when in the lectures you are taught about something called shifter. So what was it said, that when is scaling required to avoid overflow either at the input or output, at input either before addition, that is scaling by log 2 base n bits. Okay, so depending on how many extra bits you are getting, you try to multiply, you try to internally scale that, or you try to increase the register size. Okay, and that's what is mentioned after summation to get back original results, do scale up by log 2 base n bits. Process is a trade-off between overflow and accuracy that I have shown over here. Now what happens is that where I told you that we doing at some kind of loss of accuracy, there are some interesting applications. Okay, for example, this our human eye. Okay, our human eye has some kind of a persistence of vision, so it actually cannot distinguish between certain frames. Moreover, it has also some kind of locality principle, wherein our eye does not have infinite precision. Okay, because of the limitations of the rod and cone cells in our retina. Now what happens because of this limitation of our eye is that there are certain pixels which may be numerically different in our signal. Okay, as you all very well know, that image is nothing but an array of pixels. Okay, and these pixels are represented, can be represented in black and white form as a single array, or as an RGB, red, green, blue, kind of three arrays together, and each of these array has multiple elements, and each of these element is called a pictured element or a pixel, and each pixel generally represented in 8 bits, so you can take values from 0 to 255. Now the interesting property of our eye is that our eye cannot resolve or distinguish between very close pixel values. So let's suppose you have a pixel value say 147, okay, and a pixel value say 152, 5 pixel difference. Now let's, for an assumption, we say that 142 and 152 we are not able to distinguish, we feel that both of them are the same. Now how will you use this to advantage? Let's suppose you are doing some kind of a signal processing algorithm in which, yeah, I will be referring back to this, in which you are doing some kind of a mathematics, some kind of a mathematical manipulation. So let's suppose you are supposed to do some function on some number, and you are supposed to get 152, but then because of a hardware constraints and because of this scaling, just like the above, you may be lost something around just like here, instead of 30 you got 28, you are getting, instead of 157 you are getting 152, you are getting 147. Okay, so what is happening at the end of the day, you are saving your hardware because you are using lower number of bits, and also since it is a human application. Okay, let's suppose this is being used in video conferencing that we are seeing. The pixel you can see over here, the pixel you can see over here are very much the same. So some algorithm might not be working to very high precision, it might be showing this as 155, this one is 156, whereas these two could be 160 and 163. Okay, but then it does not matter to you because you are seeing both of them as the same. So what is happening, we are getting an approximation, we are incurring an error, but that error is not much harmful for the application, that error is adjustable for us. So this is actually a field called, a very important field that I feel you should all look into, is approximate computing. So what happens in approximate computing, the operations that we perform are our normal multiply, add, or maybe some kind of sine, cosine. Okay, these kind of applications we will try to these kind of operations we will try to perform, but at some reduced cost, rather than obtaining all these 7 digits or doing our entire humongous calculation. We will try to restrict ourselves to finite number of bits. So for example, just 1 hour ago I was talking to you about area as well as power requirements. Okay, so similarly area and power requirements as per application. Similarly, based on the application, we will be using approximate computing techniques where we reduce the amount of hardware, the hardware that is required for extra calculation. We will be removing that hardware for the extra calculation and saving on power as well as area, as well as we will gain speed as well. Speed is also a very important criteria for the performance of digital circuits. So based on all the three advantages, performance, and then there is not much reduction in performance because it is a human being application for human being visual activity. It might be some other applications, let's say audio. Okay, so audio also has we also have certain persistence or some kind of we don't have some issues in audio processing when you have very close values to each other. There are some kind of error tolerant, we call it error tolerant applications. Okay, but this approximate computing cannot be used always in very critical applications, like let's say when you're doing surgery. Okay, or let's say when you're sending launching rockets Chandrayaan 3 satellite launches. You cannot rely on any single operation to be wasted. You cannot rely on losing the precision. That's where you cannot utilize approximate computing. So as I always mention, always try to know the application in which you are trying to implement the system. Okay, so let's get back. I hope this discussion was clear to you. Can anybody respond?
Yeah, it is clear, sir.
Okay, so A. Hemant, Anusha Sethi, Chintu Yadav, Lloyd Morris are all of you over here. Sampath, Saranya, Shilpa, Sonali, Sri Krishna, Ujjwal Kumar are all of you in this session.
Yes, sir.
Yes, sir. Okay, so you are able to
Yes,
understand.
sir.
Okay, so all of you are able to
Yes, sir.
understand. Okay, so
Yes, sir.
so everybody was able to understand what I've been saying till now.
Yes, sir.
Okay, so if in case anybody has any doubt, please let me know. Okay, I'll be more than happy to help. Okay, so that was about shifting, in fact scaling. Okay, so the next question to you is special addressing. Which of the following are special addressing modes in DSP processors? The first option is indirect addressing, second one is direct addressing, third one is circular and bit reverse addressing, and the fourth one is none of the above. Now you can very well understand that before I ask anybody of you to answer, this is something very close to computer organization and architecture, right? So you can see very well how interesting this subject is. It's named real-time signal processing, but it includes it's obviously includes signals and systems and DSP. It includes VLSI. It also includes computer organization and architecture. Okay, so very exciting topic. I would also recommend you guys to study computer organization and architecture. I am also doing that. I will also, if required, I will share resources as well for learning these topics in depth if you want to do the same, because they will increase your holistic understanding of all these subjects and create a good profile for you as well. Okay, so can anybody answer this question? Which of the three? Yeah. So any answers? Sampath, Sharanya, Ujjwal, Sri Krishna. Which is the special addressing mode you feel?
I don't know very specific, but maybe indirect addressing.
Okay. Sharanya, your mic was on. You were you able to ask something, answer something? Chintu Yadav, Anusha Shetty, Lloyd Morris. Any guesses? Feel free. Don't worry. It's not something to be scared of. You
Direct address.
direct addressing. Okay. Anyone else? Anybody has any other try? Somebody said indirect. Somebody said direct. So there are two options left: circular and none of the above. Anybody who feels none of the above are correct? No one? Anybody who feels circular and bit reverse addressing are correct? No one. Okay, so let's see what is the correct answer. So basically the special addressing modes over here are the circular addressing mode as well as the bit reverse addressing mode. Now let me tell you why they are special. Okay, so before that we go into direct as well as the indirect thing. So let's say in, yeah, does anybody have any doubt? Yeah, Lloyd Morris, you wanted to say something? Okay. please hold a second once. Okay, so what happens in the direct, please excuse me for this bad handwriting. I will try to arrange for a good one by the next week or so. So in the direct addressing mode, what happens is that, let's suppose you want to add, you have R1. R1 is some kind of a register, let's say a 32-bit register. It has some value 0x AF, okay, dot 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 some A, okay. So there will be, since it's a 32-bit number and each hexadecimal unit consumes 4 bits, so there will be 8 hexadecimal units, okay. So let's suppose you have A1 0 4 3 F, and so there's 1 2 3 4 5 6 7 8. So these are the kind of numbers. Actually you will not get very high number. It's very high. You will actually be getting most of the time the kind of numbers that you deal with are very small. You never give such humongous numbers in your calculators or computers, okay. So most of them, let's say this is the content of R1, and maybe, and since we are talking about signal processing, we will not be dealing with even more numbers. We will be dealing with even smaller numbers. This is a CPU, that's why this is a CPU, so that's why I gave such big number. And maybe you have some kind of a memory bank, okay. This memory is the main memory, RAM, which is situated outside the CPU, okay. So this is the CPU, and here is your main memory, and then based on the opcode you are trying to fetch the content from the main memory, and main memory has lot of locations, and then there are addresses, okay. So based on the memory address bit size, you have some kind of address, say 100 something like this, okay. So you may have some kind of an opcode, assembly level instruction, which says R1 gets R1 plus mem 100, okay. So at memory location 100 some value is stored, and that value is added with the content of register R1 and stored into memory register R1. So what is happening over here is that I am directly giving the address, see the word address, and I am directly giving the address, okay. You can see the address, right? Sampath, can you see the address? What is the address?
Yes, sir. 100.
100 is the address. So basically on the 100 location of your random access memory, you try to access those bits and then add it to the R1 register, okay. So since we are directly giving the address, this is called direct addressing, okay. And another one can be indirect. Oh, sorry. So what happens in indirect is that, let's suppose I am giving another opcode, R2 gets R1 plus mem R3. I'm not exactly stating any kind of a direct ISA or some kind of I'm not stating any direct ISA, whether it belongs to ARM or RISC-V or Intel x86, okay. I'm just writing them randomly just to make you understand, okay. And these may not even be the perfect ones. To do that, you can refer to some computer architecture books in detail if you want to see the style, the syntactical style of writing these, okay. So what happens in over here is that you have the register R1, okay, Register R1 has some kind of a value, as I told earlier, some 0 x 0 0 dot 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 1. Okay, so we have this value over here. Now we have another register R3. Okay, this register R3, what happens, it contains some value a b 1 0 0 something like that. Now what is this value? This is not the value that you want to add to R1. This is the address of the memory. Okay, at this a b 1, okay, you have some value stored over here. Okay, 1 2 3 4. Okay, this value 1 2 3 4 which I have shown over here, that is added with the content of R1 and stored in register R3, sorry, R2. Let's see what was there. So register R3 has some value. That value is not what you want to add to them, but that is address of the content that you want to add to R1. Okay, so you see, Sampath, are you able to see? Chintu, are you able to see? Lloyd, Morris, Sampath, Saranya,
Yes, yes.
Sri Krishna, are you able to see? There is some kind of an indirect connection. I am not stating the address directly. The address is being stated indirectly. First I had to go to R3, then I had to check the address over there, then you have to decode that, then you go to the memory and you see that you are able to take the address from, then you are able to take the memory content from the location that has been specified to the register. Okay, this is the indirect addressing. Now what happens is that circular addressing mode and bit reversed addressing, these are not the direct ones, direct or indirect, they are quite different. Circular addressing mode will actually be used for your FIR filters. What happens in FIR filters is that you have, let's say, a 3 type FIR filter, H0 plus H1 in plus, oh sorry, H0 H1 H2. Now what happens is that you only have three tabs. Okay, and there I show them by symbol 0 1 2. But now what happens is that actually you have something called the program counter, or some which counts which instruction to be taken, and there are some memory registered numbers. Okay, from where you are trying to access. Now as the program proceeds, you will be getting time index 0 1 2 3 4 5 6. Okay, but then we have only this set of numbers, right? So at each of these cycles, let's say I want to access, at n I want to access H0, at 1 I want to access H1, 2 I want to access H2. Now I once again want to access H0 at 3. So what do you see over here? 3 modulo 3 is 0, 4 modulo 3 is 1. So at third cycle I will take H0, fourth cycle I will take H1. Okay, so H1, H2, H0, H1. Okay, so I am taking slowly and gradually as the cycle repeat. Even if the number any increments, I am taking it a modular fashion. So 0 1 2 3 0 1 2 3 0 1 2 3, sorry, 0 1 2 0 1 2 0 1 2. So you can see it's a circular mode, right? So it's called circular mode addressing. And then there's something called bit reversed addressing. So maybe I will discuss this later when I talk about FFT. Okay, in FFT we will be discussing more about the bit reversed algorithm. What happens is that actually the outputs, in order to obtain the outputs of your actually FFT, there are two ways of implementing: decimation in time and decimation in frequency. Now what happens is that in one if you want to get, let's say, x0 in the time sequence you give in order, then the frequency samples x0, a capital X0 to capital X of 7, which you obtain, are not obtained in a normal order. We obtain in a different fashion, and the fashion in which we obtain is the bit reversed fashion. So we'll discuss that more when we go to the session on FFT algorithms next week, next to next week. Okay. So now, can anyone tell me now parallelism? For parallelism, which of the following are the correct statements? First one, algorithms can perform more than one operation by increasing the speed. Second one, can do one operation at a lower energy consumption. Third one, can do one operation at a higher energy consumption. Fourth one, algorithms can perform only one operation by increasing the speed. So unlike the previous questions, this one does not have is not a single choice, it's a multi-choice question. It means multiple statements can be correct. So who would like to give it a try over here? Anyone?
It is option A and B.
Okay. So algorithms can perform more than one operation by increasing the speed. And yeah, Ujjwal, you wanted to say something? Ujjwal, Sharanya.
So it's A.
Okay, you feel it's only A, right?
Yes.
Any other option you don't feel is correct? Okay, so let's say that there is a Saranya, your mic is open. Do you want to give it a try? Yeah, Sharanya. Okay, so let's see. So is absolutely correct. Parallelism. In what happens in parallelism? Let's say you are doing one multiplication at a time. Okay, we have a single multiplier block, and that gives you one output in 1 second. Okay. So let's say you have a single multiplier block, you are giving it inputs and you are getting an output. Okay, and the rate at which we get the output, which is called throughput, is one output per nanosecond. Okay, in 1 nanosecond I am getting one product. Okay, now what will happen if I make 3 copies of this? A, B, C, D, E, F, X, hello, okay, Y and Z. Okay, so there are as you can see, you have 3 multipliers, and let's say this one is working at some particular clock rate. Okay, this has some sample frequency, clock rate, those kind of stuffs which we will be discussing later, but some kind of fixed rate at which the input is coming. Okay, which is determining this one output per nanosecond. Now can anybody tell me what is the throughput or the number of outputs per nanosecond that I am getting over here when this scenario? In this scenario, what is my throughput? Yeah, anybody would like to answer?
6 input, 3 output.
uh, okay, so yeah, actually you are not concerned about 6 inputs anyways, because if you want, if you are giving more inputs, automatically you are giving, if you want more outputs you need more inputs. So basically throughput is actually the number of outputs in every per unit time or per clock cycle. We will discuss clock cycle in the subsequent lectures, but the throughput, you say, as you say, absolutely correct, it is 3 output per nanosecond. Okay, so you can see that I am obtaining things very fast. Earlier I had one single multiplier. Now I have 3 multipliers working parallel, so I am obtaining things at a faster rate. Okay, I am obtaining, rather than obtaining one product in 1 nanosecond, I am obtaining 3 outputs in 1 nanosecond, right? Now, but then they are working at the same speed. Okay, you the important thing to note over here is that all of them are working at the same speed, and let's say, since they are working at same speed, they are consuming 1 watt of power, 1 watt of power, 1 watt of power. To total power consumed is 3 watts. Okay, now what I can do is that I can make these guys slow. Okay, so what I can do, I can make these guys slow. Yeah, so I can make these guys slow. What happens when it becomes slow, we will learn in the subsequent lectures, that actually when this operation become, see, if you have learned in basic VLSI or even digital circuits, when you try to switch fast, when you try to switch your inverter or some logic gate fast, the output also changes, right? And what is at the output of the inverter is nothing but a capacitor, and you will know very well that switching power at the output of some logic gate is proportional to the frequency of operation, the frequency at which the output of your logic gate switches. Okay, so now if I reduce the input, the clock frequency or the input frequency, then or what will happen, automatically my output will switch less slowly. I'll be able to get lesser outputs, but then what is happening, I am switching less, so I am getting lower power. Okay, so I'll be having 1 by 3 watt, 1 by 3 watt, and 1 by 3 watt. So when I reduce this, I actually end up getting 1 watt, but then my throughput also goes down. So I would say that I am operating in the same way, same rate as the single one. Okay, 1 output per nanosecond, but then I am doing that at a lower power. Okay, compared to the previous case. So that's why the answer, algorithms can perform more than one operation by increasing the speed. You have increased the speed, so you're doing 3 outputs per nanosecond, or one operation at lower energy consumption, means you are operating a lower rate, but your power consumption is also lower. Okay, so in this way you can we have, that's why you have seen that I mentioned in the content list that high speed slash low power. That's why I get that there's a trade-off, either you go for high speed or you go for low power. Okay, so parallelism, it's already been mentioned. Algorithms can perform more than operation at a time by increasing the speed, and disadvantage is that complex hardware is required to control units and make sure instruction data can be fetched in simultaneously. Now as you have more multipliers, you will require more instructions to handle each of them, so that's where the disadvantage lies. Okay, so using the Q format, the addition of 0.375 and minus 0.25, the result in the accumulator will be, can everyone do this, or anybody requires any help in this? Okay, let me do it because time is running out. Okay, so 0.375 is 0.25 plus 0.125, which is 2 to the power minus 2, and 2 to the power minus 3. So when you try to represent in Q1 dot 15, what will happen? 1 represents the integer we don't have anything, it's a positive number, so it's 0. 2 to the power minus 1 will be 0, 2 to the power minus 2 will be 1, 2 to the power minus 3, so this 2 to the power minus 1, this 2 to the power minus 2, 2 to the power minus 3, this goes to 2 to the power 0, and rest all bits are 0. Okay, now we go for minus 0.25, and how do we represent that? 1 minus 0. Sorry, it's minus 1 plus 0.75, and you can break down further into minus 1 plus 0.5 plus 0.25. So minus 2 to the power 0. Yeah, anyone having any question? 2 to the power minus 1 and 2 to the power minus 2. So in the representation, what will it be? 1 1 1 0 0, rest all will go away, and the previous one that we had was 0 0 1 1 0. Okay, so now when you try to add them, now remember, as always I said, try to do sign extension whenever you are adding. Before start trying to add, try to add extra sign bits, 1 over here, 0 over here. That will always give a correct result. So you add them, 0 and 0 gives 1, 1 and 0 gives 1, no carry, 1 and 1 gives 0 with a carry of 1, 1 and 1 gives 0 with a carry of 1. Here also you get the same case, and since it's sign extension, it will keep on carrying towards the left as always, and hence you will get this. The rest of them are all zeros. Okay, so not writing further. So what is this? This is only one is present only at 2 to the power minus 3, and that's 0.125, which is actually 0.375 minus 0.25. It is 0.125, as you might have already understood. So it's only a single one at the at the third place post this decimal. So what is the correct answer? Okay, so option A is the correct answer. Now is everybody clear with how I have done this question? Yeah. Anybody is anybody still having questions or queries about this? Because this is a very important way to solve. Okay, so let me proceed further. Okay, binary number in 1 0 0 0. Okay, there are multiple zeros. So can anybody answer this quickly? Is anybody speaking? You're not audible. Hello. Hemant, Anusha, Kapil, Lloyd, Thiruchelvelli, Sampath, anyone? Sonali, Ujjwal, Sharanya. Is my slide okay? Can anybody answer this binary number representation in 2's complement? This one should be fairly simple because this is already being done in digital circuits. Okay, so basically there are what is happening is that Hmm. 1 and then multiple zeros. Okay, so this one was I guess the 7th bit, so it will be, since it's the MSB is always the negative, so minus 2 to the power n minus 1, and this is 1, so it will be minus 2 to the power n minus 1 plus 1, and assuming n equal to 8, so it's an 8 bit number, so it's minus 2 to the power 7 plus 1 goes down to minus 127. Okay, so it's minus 127. That's fine. Okay, why would one use fractional representation instead of integer representation of numbers? Okay, so I had already explained this in very great detail in a few questions back. So can any, I guess you should be able to answer this. Can anybody please tell me? We had discussed in great detail when you were talking about the scaling question. Yeah, Sampath, any idea?
No overflow.
No overflow, absolutely. Since what happens is that, as we had mentioned earlier in scaling, if you try to increase the dynamic range, if you go for a more and more bigger and bigger integer, 4 in 4 4 we saw 4 plus 4 bit number, it was giving a 5 bit number. So similarly, if we try to do that with multiplication, we would require larger and larger spaces. Okay, but we want to keep n bit and n bit multiplication number to n bit only. Okay, because we want to save space. So in order to prevent that from happening, if we use fractional representation, then even if we lose the accuracy, we still remain in that range. Whenever fractional numbers are always lying between 0 and 1, and product of numbers between 0 and 1 will always lie in that fractional range. So you will have no concern about overflow. Only thing that will happen is that your accuracy will be lost. Okay, your precision will be lost. Okay, so very simple question. 00111 right shifted by 5 results in, can anybody tell this how what happens over here? Right shift by 5, what does it mean? Okay, so let me show you a brief illustration. Let's say the number 01101. Now what is this equal to? It's 1 plus 4 plus 8, that is 13. Now if I do 2 bit shift, okay, a 2 bit shift, what does it imply? It implies division by 2 to the power 2 or division by 4. Now see what happens. If I do 2 bit shift, what will happen? 01101. First bit goes away, second bit goes away, third bit gets over here, fourth bit gets over here, MSB goes. Now a most important thing, copy MSB. Okay, until it is 5 bits, copy MSB is 5 bits. Now what is this? 1 plus 2, what is this? 3. So basically see what has happened. When I divide 13 by 4, that's 4 times 3, 12, 3.25. But then we are working with integer numbers, so what actually happens is that we do a floor operation. Okay, we do a floor operation and we get 3. In reality is the division followed by a floor operation, because we are truncating out this thing. Because if I wanted to retain this 0.25, what I could have done is that I would have considered an imaginary decimal point and moved that imaginary decimal point here. It means you don't change the number, but you change the internal scaling factor. Okay, so that's not what we're doing. We're actually shifting it and throwing away those bits. Okay, so this is something very important to remember, that shifting right means division by 2 to the power that many bits, and shifting left means multiplying that number by 2 to the power that many number of bits. Okay, so that's what's happening in a left shift. Okay, so 0, how many ones are there? There are 1, 2, 3, 4, 5. So you will be all the 5 bits will be gone, and you will be left with only a single one. So option B will be the correct one. Okay, so how would one increase the range of numbers that can be represented in integer fixed point number? Now I want somebody else to answer this. Kapil Kumar, Anusha Shetty, Lloyd Morris, Ujjwal Kumar. Any ideas? Which one?
By doubling the size.
Yeah, absolutely. So basically, what happens is very simple. Number of bits that. Yeah. So basically, what happens is that as I mentioned long back earlier, that when you have r bits, when you have an r bit number, let's say unsigned, the same holds for signed as well. It will range from 0 to 2 to the power r minus 1. So if you double that, your size automatically doubles. Okay. Okay, so yeah, so these are the practice questions for today, and it's complete from my side. We don't have any more further practice questions. If you have any doubts regarding this today's lecture, please let me know now, and in case you have further doubts or queries, I am sharing my email ID over here. You can contact me on this email ID.
Sir, can I get Madam lectures slide?
For the slides, I think the only way to get, I think the only thing that you can do is to ask the in the NPTEL Common Forum. So basically, I am your PMRF TA. I am not handling the logistics regarding the course, like course material, anything. Course material regarding related to this PMRC. I am your PMRF TA. So these sessions, you will get these recordings in YouTube. It will be shared as well, I guess. Even these slides would surely be shared with all of you. Materials and assignment questions that needs to be discussed in the NPTEL forum. Any further doubts regarding this session, anything related to today's session, please address me separately and ask in the discussion forum. I will be happy to answer. I may not be able to answer question. I will not be able to actually answer questions that are related with your exams directly, or with your assignments and the grades. Anything, any question is correct or wrong, that I may not be able to discuss. Okay. So that's it regarding this thing, and I'm sharing my email ID with you. This is my official email ID. Feel free to contact us. C. Okay, so I guess
Can you tell me that what industry wants related to their signal processing?
okay, so
That's the profile like that.
so basically every company has different requirements. Actually, I thank you for saying that. I will also check in detail, but can you please let me know, I mean, which profile are you checking for? Are you checking for someone from undergraduate or graduate? I mean, what kind of experience do you have, or as a
No, no,
fresh?
graduate thing.
So means after doing MTech, right?
Yes, yes,
Okay. So are you a pure? You want to know from the perspective of pure fresher, right? Pure fresher graduate.
yes, yes.
Yeah. So basically,
Well,
as
I'm asking mainly related to skill set. What skill set industry wants?
okay. So basically, the skill set that's required from you is a fair level of expertise in MATLAB as well as Python, most likely Python. Okay, and these days they are favoring the skill set related to using the machine learning and deep learning frameworks. They want these things slowly and gradually. They are wanting it. It's not compulsory, but it's good to have. But the major thing that actually they check for are your projects. Okay, the projects that you have done in your master's level, and the main important thing actually they check, they finally leads to selection, is your concepts that they actually check in the interview. In the interview, they will mainly ask questions related to the fundamentals of signal processing and related coursework, but that's the interview part. But in order to get your CV good enough, you need to have good projects, and if possible good publications as well in reputed journals. I will let you know further once I check it myself, because actually speaking, this as you might be knowing, currently these we are actually in a recession economy and market, so a lot of companies are actually freezing their are undergoing an hiring freeze. So a lot of if you check out the portals, job portals of these companies, the number of job applications have reduced drastically in the current scenario. So maybe if I were to do this session a semester back, I could have given you much more examples, but now the number has reduced. So I will further let you check and let you know. But as far as I can say, the more when it comes to the interviews, they ask from a fundamentals, not much high stuff. Even if this stuff start from a project, they will finally go deep down into your basics. And for skill set, as you're saying, MATLAB and Python is a good thing to know. And in case you're applying for some of them want embedded engineers as well, firmware engineers, so they sometimes want hands-on experience with these embedded platforms, let's say STM microcontrollers and Texas Instruments, those microcontroller applications. Okay, because there are upcoming things like tiny ML, tiny machine learning, that you apply on these embedded devices. Okay, so any other doubts, any other queries, any other suggestions, also welcome. Okay, no, so I hope all of you enjoyed this session. Okay, thank you everyone. So I good night to everyone. We will meet next week. Okay.
Yeah, thanks.
Thank you, sir.